Friends, welcome to the 7th lecture on module 2, where we are going to focus on an important software application in risk assessment in offshore and petroleum industries. This is a very interesting lecture where you will get a walkthrough exercise on how to use a software application for a quantification risk assessment in a given problem. This is under the ASPISA module 2 accident modeling, risk assessment and management and HSC course organized at NPTEL IIT Madras. We will solve the same example what we discussed in the previous lectures, which I showed you the results, but now I will explain you in this presentation how to model that numerically using a software where you will get the same results as we showed in the last lectures. We are now looking at a current study which facilitates a better idea of hazards, consequence and risk involved in a specific process industry. I have taken LPG filling station as an example case study for this specific lecture. This is of course a preliminary study which will help you to understand the installation complexities of an existing plant or expanding a new one in case of the plants considering the assets located nearby the existing locality of the plant. Just to recollect what are the different failure cases and consequences of an LPG filling station, because as we understand now, identifying the consequences and identifying hazards in a given situation for a process industry is a most difficult task which requires a lot of experience and exposure to a lot of case studies. Now let us look at a LPG filling station which we already solved in the last lecture, but still we are now looking at the failure cases, the different failure modes and the corresponding consequences that arise from these failure cases. So the failure cases can be a full bore failure of an LPG outlet line which comes from the bullet. It can also be a 20% cross section area failure of an LPG outlet line which is coming from the bullet. LPG pump discharge line will have a full bore rupture. Rope tanker failure can be one of the failure cases. LPG pump mechanical seal failure can be one example where we can also do an FMEA and FMECA to reduce the probability of this kind of failure. LPG pump outlet line gasket failure, again an FMEA, FMECA can be again done for identifying the probability of failure of this gasket. Rope tanker unloading arm failure. Most of these failure cases will result in a common consequences like dispersion, jet fire, vapor cloud explosion, fireball and BLEVE. We can also look at the unloading vapor compression outlet full bore rupture of the line. We can also look at the catastrophic failure of the bullet itself. Single bullet in our design is considered as 150 metric ton capacity. We can also look at the cascading effect of failure of different bullets in series, which we call as domino effects of bullets. Most of these failure modes, as you see in this slide and the previous slide, are random. However, a mechanical seal failure and a gasket can be easily identified using an FMEA or FMECA, so that the probability of this kind of failure can be reduced. So friends, we have already discussed this kind of failure cases, different failure modes and consequences. We discussed these consequences in detail and obtained the results for different consequences for two different plants geographically located in different places depending upon the weather condition, stability class, wind velocity, humidity, temperature variation, etc. I showed you the results in the last lectures. Now we will handle the same problem using a software. Before we consider how to model this particular scenario in a software, let us again quickly look at the types of damages which I am looking at. One can also look at the effect of thermal radiation as one of the important serious damage in this kind of plants, which essentially arise from three cases of radiation intensity which is advised by Oil Safety Industrial Directorate, that is 4.5 kilowatt per square meter, 12.5 and 37.5 kilowatt per square meter. So 4.5 can result in a first degree burn, whereas 37.5 can result in a sufficient damage to the entire process equipment given in the industry. Similarly, talk of overpressure, effect of overpressure on the plants and equipments and even human body. We also see the blast overpressure variation in bar varies from 0.01, which will result in crack of windows, whereas very high value of 0.3 can cause a major damage to the structural members which can result in fatal to the people inside the structure. However, the casualty probability of these kinds of events are closer to 0 and about 0.25. This has been absolutely taken from the experiences and the case studies taken for different plants of similar location in the nearby industries. Now, once we have identified the causes, the types of damages, the consequences, now I have enough data to model this in a software and try to find out the results. Now friends, you must understand the essential outcome of QRA in this kind of study are two. One, the societal risk which is given in FN curve, the individual risk which is given as an Allar triangle or an hazard distance or an hazard envelope. Now let us see whether we are able to get these two outputs for using a software directly. Now let us look at this example where we are talking about a new problem being done in the software, which is FAST-RISC 6.0. I want to actually plan the specific location of the plant. So I select the object or the coordinates as a raster image from my system. I pick up a specific map available in the system. I select the coordinates where which I want to locate it, and I also give the east and north coordinate displacements of the system, which is entered manually in the system. The moment I say have a geographic location, I have to identify the storage space. The storage space is LPG, and I given horizontal storage unit as 1 in number. I will also locate the storage center in terms of local coordinates as given from the epicenter of this problem. I give a geographic space. Once I click this, I will be able to get the required space, the raster image of my plant, as you see in the screen now. So this has been obtained directly from the chosen coordinates from the geometry of a specific plant. Once this is done, I like to now select the material which will be involved in the combustion process. I am looking for a mixture material because LPG is a new mixture which is not available in the standard database. You can always edit the database and create your own user friendly database for the software. So now in this case I am handling this as a new mixture. I am looking for LPG. I am giving the base as molar. I add the two components of LPG as butane of 0.45 mole amount and the other component is propane of 0.55 mole amount. Then I say flammable, toxic and interaction parameters. I can always calculate the interaction parameter directly. Now you will see here automatically the interaction parameters like the flammable toxic chemical, the molecular weight, the reactivity with atmosphere, the critical temperature at which this can burn, the critical pressure, the normal boiling point and melting point are automatically obtained by using this button calculate, which is available in the software database. Once this is done, I say OK, go back to my weather class. Default weathers are available in the system as you see here. I can select the default weather as it is, or I can give a stability class varying from A, B, C, D, F, which I will now enter. I pick up a specific class. I can enter the wind velocity speed. You can see here the wind velocity can be entered manually, or can also select a specific stability class as we discussed in the last lecture. So I say stable class F. I calculate the atmospheric parameters, substrata data, then I do this for next class stability class D and 1.5 wind velocity. Then I save this as a specific file, create a study. I insert now different sources of fire like fireball, vessel rupture, levee, jet fire, which are supposed to be the consequences which I identified in the previous slide in this lecture. Now for each study, for each case, I must identify the source. For example, let us say where is the vessel located. So, I picked up a specific geometric coordinate in the given raster image and indicated that once I select that, it tells me I want to associate this with a specific consequence. Is it a vessel location? Is it a fireball? Is it a jet fire clouding? Is it an explosion, or what may be the location of the plant? So, I must select a specific study case in the geographic geometry directly from the plant and associate that with a specific kind of consequence. So, now I associate this point with vessel rupture. I also show that the explosion can be close vicinated to this location. Then I select the mixture again, which is a new mixture which is available in the database, pick up the new mixture, say OK, enter the mass in terms of participation. Please understand, we are looking for a vessel which is about 150 metric ton. So, it is 150,000 kg I have entered. Then I have given the process conditions as saturated liquid. I am looking at the gauge pressure which is available in my problem. I calculate the risk in terms of even frequency as 1.3 e power minus 5. Of course, the even frequency of a specific vessel rupture depends upon the hazard survey conducted in similar plants elsewhere in a proper location. So, enter the even frequency, then look at the scenario. The scenario can be what you see here, can be a leak, can be a line rupture, can be a catastrophic rupture, etc. Now, you have different consequences which can select directly. Now, in this case, for example, we have said it is a leak, it is an outdoor release. So, fix the hole diameter, it is 50 mm for this given problem. Then look at the vessel tank header, it is 4 meter high. Look at the location, look at the geometry, the burn data and other parameters which are required for the wind direction, which is horizontal, the explosion efficiency of the given mixture and discharge parameter. Once you do this, then do the same thing for different consequences, then run the case. Once you run, you save it in a specific location and call that file as LPG2 as shown in this example. So, now it calculates the model vessel, pipe sources, etc. for a given D class of 1.5 meter per second velocity. Then now you select the default weather conditions for calculating the risk assessment for this given problem. Similarly, now the moment you do that, you will have to now fix up the central in concentration versus distance of the given concentration of the fluid in terms of ppm. So, now you are looking for a mapping, you select the source in the given field, look for the mapping and then show this is the area where the jet fire will operate. So, jet fire will have a different radiation intensity varying from 4 to 37.5. Also give the intensity radii of the jet fire in terms of meters, the radiation distance. Can also give the flash fire envelope. For example, the flash fire envelope of blue color shows a stability class of F with 1.5 meter per second with 8696 parts per million participation in a given system, whereas the Kion shows the velocity of 1.5 meter per second, but the stability class is D. For stability class D, the humidity and temperature and weather conditions are different than the top stability class F. So, once you fix up this, it gives me a flash fire envelope from the epicenter of the given problem. Once this is done, you select the source, save the file, create a data which can be also read. Whatever you have given, the data is also available in the text form for our understanding. You can also add commentary to this report. This report can be printed and submitted for approval. Once this is done in 4 pages in this case, then we move on to the next consequence, which is fireball. Similarly, fireball, I want to estimate risk, I want to select the mixture, again it is a new mixture, select the new mixture, given the combination, supply burst pressure at which the fireball can happen, enter the even frequency depending upon the experience and case study done, intimate the fireball shape, intimate the related mass participation, which is 150 tons, vapor fraction in terms of this participation, identify the geometry from the given problem, go to the source, pick up the geometry from the picture and enter that associated with fireball, run the case, save it, get the results for all weather classes of D, F and so on. Now you will see here your contour is plotted for different weather conditions. For example, the blue one is for a weather condition of F 1.5 meter per second. The green one, which you can see closer to blue here, is again 5.5 meter per second, and yellow is further inside and so on. For different kinds of this kind of weather conditions, you will be able to get this plot essentially, which is a fireball envelope which you get from a given source. Once you obtain this, go for the next consequence with jet fire, select the mixture. LPG is a new mixture, so select the new mixture. Given the elevation at which it is going to happen, enter the elevation, enter the storage pressure and the temperature depending upon the stability class, enter the hole diameter 50 millimeter, calculate now. It gives me the angle from the horizontal you are going to enter, let us say 0, the wind velocity is approaching horizontal to the particular friction. Then you enter the jet velocity, or can calculate the jet velocity directly, enter the radiation data, look at the geometry and so on. Pick up the next explosion, go for the new mixture, again repeat the same procedure and keep on calculating, enter the flammable mass present in cloud participating in this particular problem, enter the distance of interest which you want to actually map the contour, what are the step size you want to do, give the explosion data, you can give a Mach number or you can calculate the Mach number for medium, or in this case we are doing it for low, give a flame expansion, given the obstacle density, give a ground deflection factor, the Mach number is automatically calculated, say OK. For this specific case, run the results, enter the flammable distance, get the answers and run it for all default weather conditions. Once this is completed, now you will get a new envelope where you will be able to show for different weather condition what is the explosion coverage of the specific risk. Now look for consequence and risk for the given problem, calculate the risk values for all the stability classes, default ignition set, please insert the value ignition point where you want to ignite, go to the geometry, click there, you know this ignition point, select the ignition point, give the ignition probability and operating probability, select the geometry, go to the geometry and insert the point in the geometry, go for an electric line where the source is now applied, draw an electric line, select the operating probability of this kind of failure and say OK. Now enter the default population set, insert the population set, give a population point where 2 people or 3 people may be at the plant at the working time, enter the population at that particular location, maybe 2 or 3, in this case we are doing for 2, looking for the societal risk in this case, then again enter the default population. Now enter a population rectangle where the population concentration in a different area can be different from that of the vessel, enter the rectangle. Once you enter the rectangle, the value is automatically calculated, you can always change the value depending upon intensity or density of population. In this case we are entering this value as 50, say OK. You can also create n number of such rectangles at different locations to know the societal risk applied from this problem. Create another rectangle nearby the plant, nearby the vessel in this case, have a population density different for this case. So you can change this intensity to 50, say OK and keep on entering the default population set. Once you finish this, default risk ranking point set is to be established, select this point set, go for a 2D analysis, also give a risk ranking point, select the plane boundary for the given problem where you want to analyze. So select the boundary of the entire problem, you see the boundary is being selected in the screen now. Once it is selected, it will become blue, the color changes, now the boundary is selected. Now the boundary for risk analysis is allotted to the system now. You can also group the boundary separately as you see here. You do this calculation for all weather condition, run all the rows, do for default weather condition, run for all the cases, do the consequences, do the calculation for risk analysis for all the cases for default boundary chosen for the problem. Once you choose the parameter, say OK, run rows now, run the problem, get the results. You will see on the screen now the jet fire, explosion, vapor cloud explosion all are being computed. Now you can show the graphs. The risk contour is now plotted. You can see now the risk contours available for different risk. For example, the green one what you see here shows a risk level of 1 10 power minus 7 per an average year. So, for a given population, for a chosen source, for a given weather stability class, for a given geographic location in wind direction, the risk analysis is being done and individual contours are being plotted epicenter for this particular location. Once this is done, you can also do a societal risk using an FN curve, which I will show you now. You can also change the population rectangle, go to run rows again, do the analysis back again. Now you will see the FN curve where N stands for fatalities and F stands for frequency. In this case, the green one shows the maximum risk criteria for the given problem, the yellow one shows the minimum risk criteria for the given problem as per LRP, whereas your problem is located much below the minimum risk. It means the consequence arising from the specific location in the specific plant is below the risk available to the oil and gas industry. Now if I change the population set, move it closer to the source of the value, which I will now show you. Now I go for a different population set, change the value, move the rectangle closer in my GPRS system, select a different location, move it closer, run the default population set, insert new population, insert a new rectangle which is now different from the earlier one, closer to the epicenter of the blue and red which has been shown there. Now the risk for the society will be higher, you will see that automatically in the FN curve. I also change the population to be 50, but I move the rectangle from a different epicenter now, take it industrial type, say OK, run the analysis, run the rows for all stability class, estimate risk for the default population chosen now, run the analysis, the results are now stored. Now we get the FN contour. Now you see here in the specific case for the maximum and minimum risk, for a new combination the risk level has moved from 10 power minus 7 to as close as 10 power minus 5, but still this value is below or it is much safer than the minimum risk. However, when you keep on moving the epicenter value of the risk rectangle or the population rectangle towards the epicenter of the problem, you will see that the risk is getting enhanced. So the software gives a very fine, wonderful experience of hand-on work on calculating the societal risk and individual risk contours as you saw in this example. Individual contours are plotted for different risk level, for different boundary class, for different stability class and different velocity ratios. I hope you have understood this problem clearly. So friends, we have used different types of damages, we have used different consequences, we have used different failure cases, analyzed them for different problems and gave you the results for societal as well as individual risk contours. Thank you very much.